thank you very much. And I was told by Herbert Gomler to make it accessible to young people. I only see a few, but okay. But so I prepared it so that if I'm saying something that you know well, please excuse me because I thought I should say something. So the point is that okay. So this is actually, I should say that whatever I'm going to say is joint work with Jacob Murray. Took me a long time to say his name. Murray. It's difficult for me. So there's actually two papers. One, I think the local theory, this was published a few years back in Block volume, edited by Rogawski and others. And so the global, there's a few global, there's nothing big, and we're essentially, that's one of the reasons I was in Holland for a couple of days, and this is actually, will be posted maybe in a month or so, and just finalizing something. Nothing very extraordinary, just some small things. And I also wanted to talk about it because there are a lot of things unknown still, so people can work on, so that's good. And so what is it? So the point is that, okay, so now let's see, E is an elliptic curve over F. And for me, F is going to be a number field, but in general, first of all, it could be just a field. Then I'm interested in the abelian variety, which is E dot E. And so you can look at this thing I would call TF of A, which is really the kernel of the subgroup of zero cycles on X of degree 0, which maps to the Albanese of A. Sorry. Okay, and so if you take any zero cycle, of course, over C, so since it's for a student, I should say over C, then if you have a zero cycle of degree 0, so I can tell you essentially how to do it for P minus Q. It's going to send it to an integral, if you like, from Q to P, where you take any one form, holomorphic one form on A, and then you just integrate on this over here. Of course, there is a more algebraic definition, and the Albanese variety is the smallest abelian variety generated by the image. And this, of course, has been studied very well, sometimes called the Albanese map. And I'm interested in understanding, so here, and so far I'm just looking at the field. I'm interested in understanding this thanks to some conjectures of Bloch and Bellinson. And so what one knows is that this thing here, if F is C, for example, or a field with high transcendence degree, or a large field like C, then we know that this thing here is very large. It's infinite dimensional in a suitable sense, as shown by Mumford. And if the PG is positive, that is true for any surface, but of course here for an abelian surface this is certainly true. So this is actually, so maybe I should say, true for any surface X if PG is positive. And of course if PG is 0, the conjecture of Bloch says this doesn't, so
what is true? You said something is true for any. What is true?
Oh, that this is very large.
Oh, okay.
Sorry. Yeah. So I'm saying that in this case PG is automatically positive, but I'm saying for any surface when PG is positive, this is very large. And also Bloch gave another proof of Mumford's theorem, which also works for more general fields, and by using, and he uses the generic zero cycle. Okay, so If you don't understand it, it's okay. We'll just keep to this very concrete case. So, however, the conjecture of Levinson and Bloch, I think independently says that if F is a number field, then it says that T F of A is in fact, so more generally for any surface, so this is actually torsion here. And in effect, maybe I should say why. So the reason is that, so they expect the rank of the child 0 part of A, let's say over F, this should be the order of 0 at, by the way, for any L function, arithmetic L function, I'm interested in 2 points. One is called C and the other is called E. C is the center and E is the edge. And all the numerology can be done just using these two. I actually have, yes?
So is it conjectured to be torsion
Yeah.
or actually finite?
Yeah, I'm going to come to that. Yeah. Let me just explain why. Yeah, it's expected to be finite as well. Yeah.
Okay.
That actually, maybe one has some
That's it.
control.
Sorry?
One has some control on the order of torsion, right?
Right, but it's a, well, the point is, it's a conjecture of Collier-Tallien and Saint-Cyr
Yeah.
that the torsion for this child group over a number field is actually finite. But in fact, actually, one could also use the conjecture of Bass that K-theory of any scheme of finite type over C is finitely generated. So if it's finitely generated, then torsion has to be finite. Yeah, so yeah, I was going to mention that later, but first I wanted to say that the rank here is expected to be at the center of the L function of H3 of X S. So maybe I should say A. And then so by the way, this is actually the center and this is the edge, and the distance between them is 1/2. And for half the degrees, the center is an integer, and the other half, the edge is an integer. So the conjecture is, so these two are in some sense, C is sometimes called the Birch-Swinnerton-Dyer point, and E is sometimes called the Tate point. But in any case, this order is the same as the order at the center in a different meaning for the L function of H1 of AS. And this is by Poincare duality. Tells you that's true. And this thing is really the same as the rank of the Pic 0 of A, ref. And then Pic 0 is isogenous to the Albanese, and therefore, and then, so you expect actually that everything here, child 0, A 0, ref, is captured by the Albanese, so the kernel is actually torsion. So that's actually the, I'm sorry, if it's not clear, please stop me. Okay. So it's very, and then as it was pointed out, Collier-Tallien and Saint-Cyr conjecture that the torsion in the child group F torsion is finite. So actually, so expect that the T F of A is finite because it's fine. It's torsion. Yeah. Okay. So this, of course, we don't know. As far as I know, and Spencer could correct me, I don't know this for a single abelian surface. So, and it will be really great if something like this is proved. Okay, so what Murray and I tried to do is to try to understand. So the Galois symbols. So, okay. So the point is that So now one wants to understand this. So usually the way one understands anything is by sort of mapping it to some cohomology, like Galois cohomology, and seeing what one can say about this. So the Galois symbol map.
So just before that, are there special cases of this conjecture which are known to be true? Say if you take E to be CM type elliptic curves?
No, actually no. No, it's not known for any, no. As far as I know, yeah. Yeah, of course, that's the ultimate goal, to find one case where it is true. In fact, I should say that it's not known for any surface where PG is positive. So, okay. So the Galois symbol map, where it goes is that I'll explain how it is defined. So I'm going to fix a prime here. So let's say P is some prime. You can also do it over ZP, but I'm going to do the simpler case. So let's say P is prime. And I will assume, for various reasons, bigger than 2. You can also do 2, but it's just much more delicate. And so now this goes to H2 of the Galois. You can actually map it to EP times R squared. Actually. So you might wonder where did this come from? This actually comes, okay, if somebody asks, I'll explain. I will just define it directly. I mean, in some sense, so given the child group of 0 cycles, there's always a map to Galois cohomology, H2 of the surface A, the non-algebraically closed, and Galois cohomology, and then there's a spectral sequence of Galois cohomology with coefficients like HI, with coefficients in H4 minus I into there, and then the H0 map is the degree map, and then the map to H1 is the Albanese, and then the next one is H2.
Well, I mean, you could just,
I can
like
just,
TF, you could just put my hand.
yeah, I'm going to do that.
Okay.
Yeah, I'm just saying that all that is true, but I want to do it by hand. Absolutely. That's partly why I want to do it. So, okay, so what is the map here? So now what you can do is that, first thing is that if you have, suppose, so now let's do PB and E of F. All this is really, so you can define it for any field, of course. So then what you can do is that you can look at the short exact sequence where E of F bar goes to E of F bar, multiplication by P, and this is divisible over F bar, and then here you get the kernel E of P here, and this is actually a short exact sequence of, so I write gamma F for the Galois group. And then this gives rise to, this is a well-known Kummer sequence, so this gives rise to the cohomology sequence. So you get, therefore, H0 F E of bar. And of course, this is just E of F, so same thing here. And then it goes to H1 P, and then it goes to H1 F E of F bar bracket P. So this is of course just E of F, and this is multiplication by P. And what it does is that this gives a class. So this gives a class, okay. A class, maybe I'll write P like this, which is an H1 of F with coefficient EP. So this is very much like, this is similar to associating to alpha to F star mod F star and P, a class in H1F mu P. It's exactly analogous to that. But of course here, in the case of mu P, when you go here, you get Hilbert theorem 90, and here, this is not necessarily 0. So it's not going in totally into the image of H1F EP.
So the notation is not fantastic because P is the point and P is also the...
Yeah, but it's different, right? One is capital P.
Oh, no, but it's a medium-sized P there.
Where is, which one?
To the left. Yeah.
Oh.
Wrong
How
font.
about make it script?
Okay, that's good.
Okay, all right, sorry. I thought, okay. Actually, I like...
Why are you not using the power of priming this?
Yeah, you can do all these things, but there's one theorem where we prove mod P that we don't know yet how to prove mod P to the end. So I want to set it up so that we can, yeah. Well, it's already hard enough. There are more difficulties, I agree. And then if you do all powers of P, you could also take ZP coefficients, which is what I would like to do. Yeah. Okay. Anyway, we wanted to prove something. So anyway, this is like this, but now, okay, so now you've got this class here. So therefore, you can now take the cup product P, Q. So you have two classes, P and Q, in BFS mod P. Then you can then take the cup product, and then that will be H2F P times the square. Script P. Okay. I don't want to write script Q. I hope there's no confusion with this in the rational numbers. Okay, so now what does it all have to do with T? Well, the point is that given you can always, so now given P and Q like this, now consider the following thing. You can take PQ, then you can subtract P0 minus 0Q plus 0, 0. So this is a 0 cycle on the surface, and you could take it modulo. So this is a different thing here. This is really, this here indicates modulo linear equivalence or rational equivalence. So you can take this 0 cycle class, and we can call it PQ. And by the parallelogram law for abelian varieties, you see that this thing here maps to 0 under Albanese. Yeah. So PQ is actually in P everything. You can take it mod P because we're taking everything mod P, mod little p, and this is script P. Sorry. Okay, so that actually is a map, but then you have to say something about the structure of P. So again, now I should say that this is similar to the usual Galois symbol, because so note the analogy with the usual Galois symbol. And the usual Galois symbol goes from F star mod F star to the P cross F star mod F star to the P to K2 of F mod P. And it's the same. Now here you take the class, then you take alpha beta, and then you take it to alpha, I'm sorry, not to H2 F mu P times the square, and the map here just sends it to the class alpha cup particle beta. Here. Okay, so that's the map here, and of course this map here factors through K2 of it. So in some sense our group is like K2, but not quite, but I'll explain one real difference is that, so that's the usual Galois symbol map, and this is the map, like this is the map proved first by Tate to be an isomorphism if F is a number field, and a big generalization was done by two arbitrary fields by Mercurial and Suslin. Okay, so therefore this is very similar to this here, but there's one main difference, by the way. This K2 of F, okay, this is the K2 here is the number field here. So if F is a number field, K2 is torsion, but it's not finite. But in fact, but not really finite, not finite, and then but K2 of the number field, number ring of integers, this is finite. So again, it's finite because it is finitely generated by Garland, and it's torsion by Borel. So it's always, this is the way you prove things are finite. Prove something is torsion on the one hand and is finitely generated on the other. So this is, in a way, to me, T is similar to K2O. And also, this is important because what happens is that here, if I take an OF star, mod OF star to the T, then you can actually identify, so let's say you work over a number field or a local field. So now let's say F is a local or global field. And then you could look at the model over, take S as to be spec OF. Then in fact you can identify this with H1 in the flat topology with S with coefficients in mu p. So you can take cup products and actually, so if you take the image of K2OF mod P under the symbol map, so maybe I'll call it sigma P or whatever. Yeah, sigma P. So what happens is if alpha, beta, both are units, then the symbol map on alpha cup beta, this actually lands in H2 in the, so I should say faithfully flat quasi-finite topology of spec OF with coefficients in mu p tensor 2. We have to work with flat topology and not a tau topology because multiplication by p is not a tau in when you go to characteristic p, and so it's not. So over S, then it's not a tau. So it's much better to work with flat cohomology. But I just wanted to say that, so if you don't know what flat cohomology is, since there are some people, so just think of it as defining some kind of an integral structure to the Galois
Could
cohomology.
you repeat what you said? Did you say it's FPPF? Flat? Something.
It is almost FP, quasi-finite,
Oh,
instead of finite.
Okay.
FPPQF.
FPPQ.
Yeah. All right. So, and so why am I mentioning this? Because here what happens is that E of F mod P, as I said, it's, yeah, so E of F mod P maps to H1F EP, but in fact it's in a subset of this. So what one can show actually is that if I call this map, I'm going to call, I don't want to call everything. Okay, so maybe I'll. Please tell me if I'm not making sense. Okay. I hope. Do I have to read it and so on? Is that I have to read it, right? I know I'll never get a job in Germany because once Hausdorff, this is a requirement to get a job. Okay. Oh, no. Turn, wait a second, turn the other side?
Yes.
It's like an IQ
No,
test.
No. This way, yeah.
Yes.
Yeah. I'm in trouble. Okay. Okay, this is just to stress the analogy is so what one can prove here is that so we have this Galois symbol map from P of Marty to H2 F. This is one of the reasons I want to work with number fields or local fields. You can also use some of the topology thing, and then so actually one can prove here in this case that if you take E of F mod P, this is while it's sitting inside H1F EP, you can actually prove this is isomorphic to H1S in the flat topology with EP, where this is a finite flat group scheme. Of here with generic fiber. So in fact, it is, if you work with this, then you have something smaller. So from this you can, by the way, it's not obvious actually there is a map from here to there, but there is. It's not obvious because there is actually a natural map from here to H1 flat of F with EP, I mean the restriction of EP to the generic fiber. But then there is a map going this way from here, but this turns out to be an isomorphism. So actually you have a map. So, because the map from the flat site is a étale site, so see it goes naturally this way. But luckily, whenever you have reasonable sheet, you can do it. And then you can actually show that the image of SP is actually inside H2. So if you like, it's in the image of H2 S in the flat over the EP tensor square. And this actually helped us in understanding the ordinary direction. Again, this map is not obvious, but there is one. Okay. All right. Okay, so maybe I'll say, so the idea was to really try to mimic as much as possible Tate's arguments. But it's not complete because in Tate's argument there is this nice thing that you can also represent this class in the Galois symbol, the image, it's related to, when mu p is in the field, it's related to, then you can take out one of the mu p's outside, it's the Brauer group tensor mu p, and then the Brauer group has an explicit presentation in terms of simple algebras and so on. So you can use some class field theory over there. And then one of the things we are lacking is really to understand how to describe this. Of course, here also you could base change to a field where EP is rational, and then you can write it as Brauer, if EP, so I write it is F rational, then of course the Galois cohomology, you can write it, you can write it as the Brauer group of that P tensor with EP tensor square minus 1 kind of, because you put in a mu p and so this is H2F mu p. Once EP is rational, mu p is also rational because mu p is actually the determinant of EP by the Tate pairing, by the Way pairing, sorry. Okay. But it's hard to use that actually explicitly in this case. So what one really would like to do is to really understand something like H2FEP, something. We don't know that. I've tried a lot to try to understand it. It's not, doesn't seem possible. So let me actually try to give you a few, maybe I'll give the main result. Again, it's with Murray. Okay. So the first thing is that, so now let's assume E is a semi-stable vector curve. So F is a Lambda field. Elliptic curve over F. So there is no additive reduction. And additive reduction, maybe it can be done. I have given it to a student to try to do it, but it's actually delicate. It's not trivial. It's not obvious what happens. Okay, so what are the steps here? The first thing is that yeah, suppose that for every place V dividing P, again, let's assume P is an odd prime. There is a statement for 2 as well. And so the really key point is, yeah, maybe I should say here, once I go to the number field, of course, I'm going to look locally what happens, and then look at the global local abstraction, which is non-trivial a priori. And what happens is that locally you can show that for any place V of F, and the only really bad places where the image is non-zero locally are the places which lie above P or where the elliptic curve is bad reduction. So those are the only ones. So otherwise it's, so even though when you try to go from global to local, it's not all the places, it's only the places, finite number of places which lie above P or where P has a bad reduction. Okay, so now for every P you assume that either E has ordinary, or I'm putting multiplicative reduction, or I'm going to assume that he has super singular reduction, but in this case I have to assume with V, FV unramified. In the ramified case, it's quite difficult, and it's really not complete, and it's not. I'd like to say more about the ramified case, but it's quite difficult because okay, then one can prove that the image. Sorry, let me also assume here. I have to make an assumption here. That is not true. So assume so let's assume 1 or 2, assume in 1 that mu P is not in F. So what I mean is not F rational. If EP, it makes a big difference whether this is a finite Galois module, whether it's semi-simple or not. Semi-simple and yeah, that's it, yeah. So in 1, assume that this is EP is not an F, EP is semi-simple.
Well, are they two is's? Is, EP, is, semis,
Yeah.
or is one an in?
One
Sorry?
if.
What's that?
Sorry?
Yeah,
No, just,
Yeah.
there's two things that look like is there. What
One
was
is
that?
an if.
Oh, if. Yeah. I have a kind of lisp in writing. Sorry. You're right, yeah.
Your
Okay.
handwriting is terrible, yes.
I apologize.
No, it's okay.
Okay. I would rather have the math be correct and handwriting bad than the other way. Okay, all right. Then in this case, the image of SP is 0. But it is semi-simple, by the way, and the BP is in there, then the image is actually not 0 in the ordinary or multiplicative case. But in the super singular case, I don't know. So in the ordinary case, let me just say here that it turns out that the image is at most one-dimensional. It's either 1 or 0. That's very important.
Sorry, what's it most one dimensional?
In the ordinary or multiplicative case, the image of SP locally is one-dimensional. At most one-dimensional. It's 1 or 0 dimensional. Whereas in the super singular case, you could have two-dimensional a priori. I don't know. It happens, but okay. 0. Okay, that's the first thing. And then the second thing is that suppose we have a class in T at the way mod P. Ah, sorry, I forgot to mention something very important. I will mention it after the theorem. Okay. Has 0 image, has image 0 under SP. Then theta is everywhere locally trivial. i.e. theta belongs to the kernel of T f of A on T to all the places where I get T, F, V, V if you like. So if something goes to 0, I would like to say it is 0. That's what Tate proves in the multiplicative group test. But I can't prove this. But we can prove that if it is 0, then if it is non-zero, it's going to be an obstruction to kind of Hausdorff principle.
So it's probably sort of all V of all primes, not just...
All V and all prime. Yeah, exactly. All V.
The other part, by the way, why do you want P not equal to 2 here? And where is it used?
Oh, where is it used? Well, some places it becomes a problem. We are looking. I'm going to come to maybe symmetric square, and it's not well behaved.
Okay.
And P is 2. And one can say more with P equals 2, that it's just more messy. So I would rather not say. Okay, so that's part B. And as I said, I forgot to say something. I will say, but also part C I want to mention. Okay. I think it wasn't too bad last time. Oh God, I thought I was done. I was already stressed. Okay. Okay, sorry. Okay. It's actually not bad. Right. Thank you. Right. So, and then there's part C. Sorry, maybe I'll explain part C a little bit after this. So the point of part C is that, so now assume, so suppose there exists a plate V about P where P has good ordinary reduction. Then there exists a finite extension K of F. If you want such that if I take K and then the degree of this over, you can adjoin EP. So this means the field over which EP becomes rational. This is at most 4. And again, 4 and points P, Q, and E of K, the global point, such that SP K over K, not of this symbol PQ, and 0. If we allow a little bit further extension, and let me just write here, we may even choose one of the points to be torsion. So if one of the points is torsion, it's easy to see that then this is torsion. So, so this answers one of the questions Collier-Talon and Saint-Sucre raised: are there non-zero torsion points in T? So this is, so there are some, so at least this tells you that the image is not always 0. So it's important because it will be kind of bad if the image is always 0. So that's one of the reasons I didn't want to work with things tensor QP. When you work with QP, then you expect the image to be always 0. Whereas here, when you work with ZP or even mod P, the image is not always 0. But of course, it should still be torsion. So that's it. But now I forgot, now I'll explain one thing. So maybe I should make a remark here, that what is TF of A? I gave you elements in TF of A mod P, but I made it look like it all consists of symbols. If that were true over F, then you can prove finite generation, because by Nadel theorem, the points are finitely generated on P. So we have to really take something called the symbolic part, and this is really the one, the group generated by symbols, PQ, with PQ and EF. But the simple proposition says that actually that TF of A is really generated by the norms from K to F of S, T, K of A on P for all finite extensions K over F. So this is different from K2 in that sense, right? Because K2 of a field is generated by symbols coming from elements just over the field itself. But here they come from. So one of the results that follows from, or we can show that one can show examples where TF of A mod P is larger, not equal to ST. Essentially, you can take an elliptic curve which has rank 1 over Q, and so there is only one, and then let's say even ignoring torsion, so points. Then what happens is that the basic fact is that P, the SP of P, this is 0. So P, this is another reason. If P is 2, that is not true. It has order 2. You have to carry that around everywhere. So this is kind of a skew symmetry. So if your E of so if E of F, so if E of F, for example, is Z, okay, across some group which is prime to P, torsion prime to P. So anyway, let's just say Z for simplicity, then the ST F of A must be 0. But T need not be 0, and we can show exactly where it's not. So that actually was what makes it difficult. But, okay. Alright, so I think I only have 10 minutes to do. So maybe I was thinking, okay. Since 3 is what we did as the last, maybe I'll indicate how we do it. And it's also the shortest. Some of the proofs are long, unfortunately. But I can explain how you get elements here. So anyway, so idea now, proof of part C. Yeah. So anyway, this is far from what we want. We want the kernel to be, like finite. So we would like actually the symbol map to be injective, just like in Tate's case. And I think it is true, and I think it's even conjectured by Somekawa and Kato somewhere. It seems like that, in fact, it should be injective. The Galois symbol map won't be surjective, because it should be only the integral part in some sense that comes to the image. So it should be surjective onto the image coming from the flat thing. So anyway, how do you prove this? So this is kind of fun. So I can say...
Sorry, at this point, K is global? Or?
Sorry? K is global of F. F is global, yeah. F is a number field.
Okay.
Oh, yeah. By the way, in this thing here, the difficult thing, there are two difficult things here. Oh, yeah. So here, one of the difficult, okay, I don't know if okay, if somebody asks questions, I'll answer. So there, the difficulty is, there's not too much difficulty. When you have supersingular reduction, the Galois representation is irreducible in the unramified case, EP. So if you take so one of the things you notice, maybe I should make a remark here, even before I do this. So you can take H2F, the covenant BP tensor square, and then it has, you can also go from there to, this thing is a direct sum of the symmetric square EP, direct sum the determinant, which is just the mu p. This is the determinant. So when you go from here to H2F mu p, and then you look at image of SP here, so you have SP, this composite map, if we call it SP bar, this map is 0. It just skews symmetry because this is big, because PP goes to 0. And this is the exterior, if you like, this is the exterior square of EP. So in fact, so that's the reason. So you really have to go to the symmetric square, and H2 is symmetric square. And so locally, if you take over FV, then your local duality, you can take H2 FV with coefficients in the symmetric square of EP. Then by the local duality, this is the same as H0 of FV with coefficients in the if you like, the Cartier dual, like this. And this Cartier dual is what one calls the adjoint representation in this case. So what happens in the supersingular case is that the adjoint, so anyway, whenever this EP, the representation is irreducible, this adjoint cannot have any Galois invariance. So that's what happens in the supersingular case if the field is unramified. And the case of ordinary, I should also say, by the way, very important, the multiplicative case here, I put it in together, but the multiplicative case was actually done by Yamazaki before we did ours. He did the multiplicative case. Well, he did the split multiplicative case, and there's a tiny bit to do for the general case, but it's not a problem. Again, not a problem for P equals 2. P not equals 2.
I'm losing the thread. You want to prove C?
Yeah, I haven't started yet. I just wanted to say, first of all, I go to this. Yeah, sorry. Okay, now I have 7 minutes to prove C. Did they actually start at 11 or 11:02?
11:05.
11:05. Okay. I'm sorry, I just want to, I think it's not. Sorry? Yeah, like, you guys have to give us a break for erasing. Third time. I think Schumer caved. I'm not happy about it, but anyway. Not very soon, people will be tweeting their results. Objections, answers, everything will be tweeted.
Don Zagier can be the Trump of math, tweeting results.
Oh, no. Okay, all right. So the point is that, okay, so now I'm going to talk about proof of C. So first of all, this is the lemma from non-Archimedean geometry. So let's say here K is a Q. I'm going to assume characteristic 0, may not need to. And so now the lemma is that let F be some morphism of algebraic variety. So this is approximations, maybe let's say smooth algebraic varieties. Defined over, so everything is defined over K, and let P be x of K. Sorry, I like P, as you might have noticed. P prime, let's say, is f of P, which is in y of K. And if f is at all at P, then this is a, I didn't know this till I actually heard this guy. I don't think of it in terms of non-Archimedean things. And then there exists in the analytic topology, the theoretic topology, which will be a standard result. Neighborhoods U of P inside x of K and U of P prime inside y of K, okay, which are neighborhoods of P and P prime respectively.
Your P's are slipping.
But there's no prime here. Oh, okay, I could have said non-Archimedean.
U of P.
Non-Archimedean local filter. So there's no.
U of P.
Yeah.
No, but that's
This, I'm saying that.
Okay.
I'm saying that the only P's are points here, not primes.
No.
They call that P.
I thought no, it's P. Sorry. It's a purely geometric analytic statement. It's nothing to do. Yeah. Okay. Sorry. Respectively. Then so such that this f restricted to u of p is an analytic isomorphism onto u of p prime. This is in this book by Bosch and God, I cannot ever remember the second one's name, Remmert. They have a book called Non-Archimedean Analysis, and this is on page 302. Not precise. So this is something reasonable, right? I mean, okay. So now we just use this, but we have to be a little careful. At least I have to be careful. So, okay. So you want to apply this. So now here's the proposition. Essentially, I'm going to globalize the points and then globalize the symbols. That's all. So it's not very difficult, but you have to, of course, check it's non-zero. Okay. So now let P1 be in E. So of course we are interested in now K to be FB. So we take P1 to be E of FB. And then let's say P, and P1, let's assume it's an odd and E of 2. So 2 torsion. So then there is this extension, finite extension K of F, and a place W of K such that KW there are always degree 1 primes, which you can take degree 1 over V, and a point P in E of K is kind of like such that P is congruent to P1, if you like modulo. I would write mod P, but what I mean is mod P of E of KW. Okay. Okay, let me just say what the idea is. The idea is, truth is very simple. You just apply this lemma to 2 different situations. Apply lemma to, first of all, multiplication by P. Now it's a different P. So you take this map here, which is it's a étale map. FP is so in this case. So so you can apply this here to now apply this to get neighborhoods U tilde of P1, and P1 now hold on, you have to be very careful. So, I'm running out of trouble. Do you believe this proposition, or then I'll just
Maybe we can ask.
wait? Okay, so essentially the point is that if you take what we have to do is that we have to take a point R in E of T of F3. And I'm going to assume here that which in the theorem it's assumed is that E, we can always, by base changing, we may assume that ET is contained in F3. So that's just taking a finite extension. And the point is that if you take any point that's in EP, and then let's say R is not 0, then under this map, multiplication by P, this goes to 0. So you can think of this R as this point P is script P, and this is the point script P prime. Then you can get neighborhoods U tilde of R and U tilde of P prime, which is U tilde of 0 here. And I'm going to take U tilde of my point P1 to be this U tilde of 0. Maybe I should put a prime here. Plus P1. So you just translate this point. then you have to apply, the next thing you have to do is to, I wish you were had a quick, can I use the other eraser? Since I'm only going to write for 3 minutes. Sorry. This is a lot quicker. Okay. Okay. So then you can also apply to it's important I start with an arbitrary point P1, and now next apply lemma to the double cover map E to P1, and of course E2 is the thing that goes to the ramification locus. So that's why I wanted to take P, then I took P1, P0, and P2. So therefore here you see that this thing here is étal, this is étal at P1. And then you can now take neighborhoods U of P1, and then what it maps to here, then it just maps to U of x1 if you like. If you write this in coordinates with x1, y1, or y1 squared is some phi of x1, it just goes to x1. Now, okay, I'm really going fast, but the point is that I can also shrink it, can shrink this U of P1 to lie in the U tilde of P1 that you have over here. And then you have to check that everything works. It's actually something non-trivial, and moreover, because now you can when you throw out the E of 2, it's an affine thing, it goes into A1 here, and because it's an A1, you can actually assume that this thing here is, so this thing here we may assume that U tilde of x1 is a unit ball. So because it's affine, you can assume that it's a unit ball. So once it's a unit ball, then you know that it contains f points, the global points, x, and then you then lift it. It's important that you have a unit ball. In the p-adic, then the f points are dense, so you can find f points, and then you can now lift it to a p, which also is an f rational point. You get a p in E of f, E of k, or p. Yeah. Yes?
Wait.
Yeah.
What are you saying? I mean, it's true that it's locally p-adically a ball,
Yeah.
but the structure is not the...
No, but I've arranged it so that for any point, so the arrangement is that for any other point, this thing here is arranged so that this, because of the two intersections of the two open sets, once you fix a global point, which is inside this U tilde of P1, then it's going to be congruent. This global point will be congruent to P1, not P. I'm just saying that you can find a point, global point that's congruent to this. So then I do the same with Q, but then I have to use local arguments. So that's why I wanted to take an arbitrary. I can find an arbitrary points P1, Q1, so the symbol is non-zero locally. Then I can lift it to get a symbol globally, and it's non-zero. Okay, all right. Let me stop.
So questions?
I actually just had a comment. You said that this thing is analogous to K2. Or
K2 O. Yeah,
O.
right, yeah.
Yeah, and I've always wondered about that, because let me tell you why I've wondered, and see if I can say it in words, if not, I'll just...
Yeah.
But you have two kinds of relations in these guys.
Yeah, I can erase so you can write.
Yeah, oh, okay, I already know. I mean, I'm good. I'm good at that.
You're saying Dinakar's not?
Well, Dinakar's learning.
I'm learning it, it's true. I haven't been to Germany that often.
No, you raise a really interesting point. So you're saying that K2 of OF
Yeah.
This is sort of like, this, you would call AF?
No, TF of A.
TF of A?
T is the organizing
T,
term.
yeah, I'm sorry, I had my letters. TF of A.
Yeah.
Okay, now the thing is that, and let's work mod, because your discussion is mod constant, so let's say mod L or mod L. Let's say, mod L.
Yeah. Yeah.
Okay, mod L.
Right.
Now, here, and these guys have this property that they're bilinear, and you have a norm. So the two
Right.
things,
There.
bilinear
Right. Right.
plus norm,
Right.
okay? And that
And it's
imposes...
even skew symmetric.
Right,
Bilinear.
well, okay,
Yeah.
we'll get into it, but
Yeah.
this imposes automatically some relations. Namely, if I go up, so if I have an element T, and I go up to F adjoin the Lth root of T,
Right. Right.
then I have the symbol,
Right.
well, let's call this symbol U, then I have the
Yeah.
symbol
U.
U to the L, comma,
Right.
1 minus U,
Right.
and its norm is, no, that's not what I'm trying to say. The relation,
Right.
what I'm claiming is that T, 1 minus T, is automatically in L. I mean, if you didn't know the Steinberg relation,
Right.
this is automatically in L times K2
Right.
of all F, simply because 1 minus T is a norm.
Right. Right.
And the bilinear and norm imposes the relation that you have automatically that, okay? Now this guy has the same
Similar
thing,
property. If
but
a-
the difference,
Yeah.
or maybe the difference, or this is the question I would raise, we know the Steinberg symbol is the whole story. Those are all the relations,
Right.
right? So mod L, they are also all the relations. So all the relations come simply from relations forced by bilinearity and norm.
Right.
Now, over
Those
here,
relations are also forced here.
those relations are also forced
Yeah,
here,
right.
but it's not clear that those are all the relations. That's the question I would raise. Are all the relations in here simply those forced by bilinearity and
Yeah.
norm?
The one other difference is that here you take the Lth roots of T,
Yeah?
and here you have to take the Lth root of a point.
Yeah?
And the Galois extension is different.
Absolutely.
The Galois group is, that's what's harder here. It's
There's
E
no
of L.
obvious
That's
Steinberg
right.
symbol.
No.
It's much deeper. But it's still not clear to me that it's wrong.
No, it's not wrong, yeah.
I mean,
No,
you
no,
know,
no,
it's a
I
much
very
more
much hope it
mysterious
is true, and
yeah, it's a much more mysterious situation.
yeah.
There is some work on Kummer theory on abelian varieties, but
Right,
it's
right. I use that actually